Okay, so the problem at hand here is we are supposed to show all of the following. That finite subsets of the real numbers have measure 0, that countable subsets of the real numbers have measure 0, and that the set of rational numbers has measure 0. We can note that Q, the set of rational numbers, countable. Additionally, finite sets are countable. Therefore, sufficient to show that countable subsets have measure 0. We start by considering a set S which is countable. We'll do x1, x2, x3. It says countable, not finite, so we do not have an xn here. One other thing that we have to note here is that xi does not equal xj if I does not equal j. This is another way of saying each element listed out here is distinct. Now, recall that we have the definition of measure 0 here. What we are trying to find is a set of open intervals such that S is contained within the union of all of these open intervals, and that the sum of the measure of each individual interval is less than epsilon for any arbitrary epsilon greater than 0. So we're going to have to be careful with how we construct our intervals here. We'll consider that for any natural number j, the value xj is contained in the interval defined by xj minus epsilon over 2 to the j plus 1 and xj minus e or epsilon over 2 to the j plus 1. So this is just clearly a minor shift to xj as the lower bound. Oh, excuse me, that's a plus. And a minor increase as the upper bound. And it's trivial that xj for every j will be contained here. So we can note that because every xj is contained in an interval of this nature, S must be a subset of the union from j equals 1 to infinity of each xj minus epsilon over 2 to the j plus 1 and xj plus epsilon 2 to the j plus 1. So we have proven the first criteria here. So now we just need to show that the sum of the measure of each individual interval is going to be less than epsilon for any arbitrary epsilon greater than 0. Then we can note that the measure of each interval is the following. It will start here, xj plus epsilon over 2 to the j plus 1 minus xj minus epsilon over 2 to the j plus 1. We can see that these xj's are going to cancel out, and this negative sign is going to turn into a positive sign. So we have measure 2 times epsilon over 2 to the j plus 1, which equals epsilon over 2j for every interval. So we can now write the sum of all of the intervals as the sum from j equals 1 to infinity of epsilon over 2 to the power of j. We can now pull the epsilon out, so we have this. And this is a decently well-known result that this value converges to 1, so we just have epsilon. And since epsilon is any real positive number, the result follows, and we are done.